All right, welcome back. It's my honor to introduce our next speaker, Professor Johann Wang. Johann is a professor in statistics at Seoul National University. And Johann has made substantial contributions to optimization, machine learning, and high-performance statistical computing. I had the luck to collaborate with Johann on a few projects, and each time it's a great learning experience for me. And yesterday he told me they are figuring out a way to invert huge matrix on supercomputer. I'm very looking forward to Johann's talk today. I suppose you will cover that. Yeah, I'm looking forward to it. Thank you, Johann.
Okay.
Yeah.
Thank you for having me, and thank you for a nice introduction. And yeah, so I'm going to talk about how to invert a huge matrix in this talk. So this talk, as the title suggests, is about high performance computing and also for statistical computing. So high performance computing, according to some textbook, means computations that are so large that the requirement on storage, main memory, and raw computational speed cannot be met by a single, say, desktop computer. And we are statisticians, and so we have to think about statistical computing. So by high performance statistical computing, I mean conducting large scale statistical computation by efficiently engaging those HPC or high performance computing devices. The organization of the talk is simple, 3 sections, and they are organized also in a historical manner, reflecting my experiences with GPUs and cloud computing and supercomputing centers. So the first, GPUs. This is probably the most latest NVIDIA GPU of the time, RTX 4019. But my first encounter with GPUs goes back to almost 20 years ago. So as an electrical engineering graduate student, I was involved with a class project, something related to data compression. And I got interested in this compression domain volume rendering. Volume rendering is a scientific visualization technique that basically inverts tomographic imaging, which can make a substantial contribution. And here, volume rendering basically computes this line integral to compute the pixel intensity at some location, which is basically integral along a ray in the viewing direction of the volumetric scalar field, which is summarized as a C of t in here, and there's some attenuation coefficient which contributes the value of the pixel intensity of the final value. And there is a need for data compression back then because, let's say, it's a quote from a 1992 paper that 512 by 512 by 512 volume of 8-bit sample requires 134 megabytes, a quantity that is usually quite problematic. Yeah, we remember that it's in the 1990s. Yeah, 100 megabytes was problematic, but now the same problem occurs with just the different units like terabytes these days. Yeah. So these authors of 1992 paper consider the vector quantization for volume rendering, which is basically about dividing this volume scale, the volumetric field of size L times M times N by a continuous blocks of size I times J times K. Then each block is treated as a vector in the Euclidean space of dimension I times J times K, and that is quantized according to, say, 8-bit codebook. In statistical terms, this is equivalent to K-means clustering, with 2 to the 8 centroids, and do a nearest neighbor mapping to the nearest centroid. Then that makes an effective compression of the data. So you compress the volume to a size of L over I times M over J times N over K. And you use the index to those 256 2 to the 8 centroid. So that's a compression. And also you need a space to store this 256 quadrants, but that as a manageable size that can be fit into the memory. Then you can find this scalar value basically by table lookup. So you have an index. You basically do some index calculation, and you look up the centroid called codebook. So that's the basic idea of the spectral quantized volume rendering. And the goal was to render the scalar field in real time at an interactive frame rate, say 15 frames per second. And back in the early 20s or 21st centuries, GPUs were basically about these 3 tasks. It has a hardware-assisted texture mapping, and it has an internal texture memory. And it has 2 sorts of programmable shaders. One shades a geometry, one upward, supports programming the vertices of the polygons that the GPU is rendering. And the fragment shader basically computes the pixel values. And for real-time volume rendering, that compressed index arrays is stored in the texture memory of the GPU. And the vertex shader basically computes the coordinates of these index. And the fragment shader fetches the code word or the centroid from the index and then computes the interval. Then what is remarkable about GPU is that it can run these shader programs in parallel for every pixel that it renders. So even in 20 years ago, it was parallel hardware. And this is a sample fragment program that does this computation. It's written in something called OpenGL. And you see it does integral computation, but it's all written in the language of computer graphics, like a texture, coordinates, and colors. But in a nutshell, it computes an integral. So it's an early instance of so-called general purpose GPU programming, or GPU. And in early 2010s, when I became a statistician, I encountered this paper written by those who spoke, all 3 those who spoke prior to me, right? And there was key change between 2004 and 2010, or early 2010s. There was a CUDA back then. Before, in 2004, there was no CUDA. So I have to write all this OpenGL program. But CUDA made this GPU program much easier. And also, I had a great student to work with. So the first project that I got into with GPU was this fuse-lasso computation. It is very famous model, but to repeat, it's a sparse regression problem with a certain grouping among the coefficients. And probably the most famous one is one-dimensional fuse-lasso, where you group the coefficients in an adjacent coefficients, and with that corresponds a chain graph. And that can be generalized to more general graphs, like a 2-dimensional grid, which has some applications in imaging. And it is a difficult problem because this second penalty, L1 penalty, is not separable in the number in the optimization variables. So it's an interesting optimization problem as well, and especially when the dimension is large, say greater than 100. And this is an only two-dimensional fused lasso regression result that I worked on brain imaging. It is called image-based regression, where the goal is to predict some human behavior response to some visual stimuli based on the functional MRI measurements. And here, the dimension, even though it's these are slight, very small thumbnail images of 100 by 100, in dimension-wise, it's a 10,000 dimension regression problem. And the sample size is like 300. And the goal was this project was to identify some active regions in the brain that correspond to the sensory motor and associated cortex regions. And as you can see from the previous slide, this two-dimensional fused lasso successfully located some two contiguous regions in the brain, and that is confirmed as correspond to left and right primary motors that plan movements in association with other motor areas. And this is consistent with previous brain research. So to do this science, what I used was, not surprisingly, the algorithm. And this is for a one-dimensional fused lasso. And as most of you are familiar with, the algorithm is some majorization technique that gives a surrogate function that you minimize in every step. The surrogate function I got end up with is this complex-looking one, but this is based on our afternoon speakers work in 2005 for a plain lasso. So it's an extension of plain lasso MM to fused lasso MM. And it turns out that minimization of this surrogate function in say alt iteration reduces to solving this symmetric, positive, definite linear system, which looks pretty much like the normal equation of linear regression. And Ken would prefer sweep operator, right, to solve this. But for some reason, I chose a preconditioned conjugate gradient, which is quite well studied to solve this sort of system. And this part I named MR. This MR matrix has some property that it is just a tri-diagonal. It's a sparse matrix. And preconditioned conjugate gradient, or PCG iteration, looks just like this. I'm not going to go into the details, but the most prominent feature of this PCG algorithm is that the iteration, most of the iterations steps are made of matrix vector multiplication. And GPUs are pretty good at doing matrix vector multiplication. So I use that feature, but there's a catch. Because I used a preconditioned conjugate gradient, it needs to solve some matrix equation. So this part, the third step of this iteration is the bottleneck in parallelizing this computation. But if I use this MR matrix as a preconditioner, because it's tri-diagonal, there is a solution. There is some algorithm called cyclic reduction, which can solve this tri-diagonal system in parallel. And that's fortunately implemented in a CUDA library called cuSparse. And the specific function name is also available. So that was a savior. And I was able to get, say, 12x speed up for 20,000 dimensional problem. And then I got into this 2D fused lasso problem. That's actually used for this image-based regression problem. So for 2D fused lasso, I was able to develop a new, similar surrogate function, just like that 1D case. But it turns out this MR matrix is now block tridiagonal because of the 2D structure. And there's a block version of a cyclic reduction algorithm. But implementing that algorithm on GPU was not very practical. This was because every reduction step of the cyclic reduction involves another, actually three more tridiagonal system solve. So doing that in parallel was not very effective. So I turned into another algorithm called ADMM, Alternating Directions Method of Multipliers. And it also involves the PCG step, but in this time, this MR matrix has much simpler structure involving the identity matrix and some matrix I named A. And A matrix has again a block tridiagonal structure, but it's much simpler and have a specific values on this diagonal and off diagonal. And it turns out that it has to do with the two-dimensional discrete Poisson equation. And discrete Poisson equation can be very efficiently solved using Fourier transforms. And for this case, it's a 2D Fourier transforms. And also GPU can make this Fourier transform very efficiently. So that was the main workforce for image-based regression. But there was another technical limit. That's the memory. Yeah. Most GPUs back in 2015 had memory less than 6 gigabytes. And if you think of 256 by 256 image, and if we have enough sample size, that basically frees up the memory. So if you want to do some large size problem, you got memory bounded. So there can be a solution if I use multiple GPUs. If I use two GPUs, that's 12 gigabytes, 3 GPUs, 18 gigabytes. Okay, so that will solve the problem, but not really. Because that means I have to implement some distributed matrix vector multiplication because the data are distributed among GPUs. And in GPU computation, the major bottleneck is the data transfer between CPU and GPU. It's pretty slow. Yeah. So if you have to use, if you have to go through CPU from one GPU to CPU and to another GPU, that's a bottleneck, really slow bottleneck. So you need to avoid that as much as possible. And fortunately, back then, there was new technology called GPU Direct that those GPUs can basically communicate without meddling of CPUs. So GPUs connected to the same, say, PCI bus can bypass the CPU. So that was another savior for my project. So then now the problem reduces to implementing this distributed matrix vector multiplication. So here you have this data matrix X. You divide that by by row. Say you have 4 GPUs, then you have 4 pieces. And if you want to multiply a vector B to X, then it's simple. You just need to multiply that. You just distribute the same vector to each of the GPUs and multiply with the pieces that each GPU has. And then you just gather the result and concatenate to get the final result. Okay. But I also need to multiply a vector with the transpose of the data matrix in the PCG step, and that involves that's a little more involved. You need to also distribute the transpose of the data matrix, but you also need to split your vector into, say, 4 pieces, and then distribute the pieces to each GPUs, and then multiply. But that's not the end. You have to gather those results, and then have to sum them. So it involves more communication and more gathering step and the summation. This operation is called reduce. If you are familiar with the map reduce, that's the same reduce operation. And in this case, it's particularly sum reduction. So these have to be programmed using CUDA and GPU Direct. That was a major task of the project. And the result is shown in this busy plot, which I'm not going to go into the details, but the basic take-home message is that using these techniques, I was able to get up to, say, 400x speed up. And also another message is that if you have large data, single GPU just refuses to run. So you do need multiple GPUs. Okay, the next section is about cloud computing. And this is based on my collaboration with UCLA folks. Yeah, and Seoul was my PhD student, and now he's a postdoc for Ken and Hua. So as time goes by, say since 2015, I had the demand of analyzing much bigger data. So those data doesn't even fit to multiple GPU memory. Consider UK biobank data. Yeah, so that doesn't fit into the GPU memory, most of the GPU memory. If that's the case, there are 2 possibilities. First possibility is to carry out computation by moving partitions of data back and forth between GPUs and CPU. I told that it's a major bottleneck, right? So that's not very feasible. Another possibility is to build your own cluster with a high-speed interconnect. So that's practically a supercomputer. Yeah, this solves most of the problem. It's more scalable than GPUs and works even when the data do not feed in the main memory of the computer, not the main memory of the GPU. But expensive, right? Then I figured out a possible cost-effective way of doing this computation, and there was this big tech companies who, like Amazon, Microsoft, and Google, who lend their practically infinite amount of computing resources to users on demand. And charge by CPU time. And they basically sell their resources by wrapping them as a virtual machines. The implication is that if I borrow, say, 1,000 virtual machines and use them for 1 hour, that costs almost the same as the cost of using one virtual machine for 1,000 hours. So it's quite cost-effective way of getting, cluster and building it on the fly, right? So that was an attractive option, but there was a catch. That you have multiple virtual machines that can talk to each other doesn't necessarily mean that it's highly performing. You need very fast interconnect that those virtual machines can talk to each other. It was not very feasible until like 2016, 17, but starting from that, there was actually many improvements made by these companies. Yeah, that made this HPC on clouds feasible. So, for example, Amazon's C5 instance, our instances are equipped with Xeon Platinum CPU with 18 cores, which is quite good, and 44 gigabyte RAM. And the most importantly, the network bandwidth is increased to say 25 gigabytes per sec. So that's pretty fast. So I can conceive some fast working virtual supercomputer. And there's also storage support. And if you have more money, then you can get the faster CPU and faster interconnect. So it has become a viable option for, say, high performance computing. And also there is a resource manager for cloud, which has a similar functionality to job schedulers for physical clusters. So times basically appropriate. But there comes this programming burden. Yeah. Unlike multi-core GPU workstation, this virtual cluster is a genuine distributed memory system. That means that processors have their own memory address spaces and cannot see each other's memory. So they have to communicate in some way explicitly. And this explicit communication mechanism is now almost standardized in the name of message passing interface, or MPI. So I need someone who is good at MPI programming. Yeah. To just introduce briefly, MPI calls consist of point-to-point communication calls, like sending and receiving data between, say, two processors or machines, and collective communication calls like a scatter, which we have just seen for the multi-GPU implementation, and gather, which we have also seen, and reduce. In addition to that, there's broadcast that one processor sends data to all other processors, and all gather and all reduce, which is basically broadcast version of gather and reduce, which we have seen before. But still, it is cumbersome, especially for us statisticians. Like we are casual programmers, not not software engineers. Yeah. So I looked into the deep learning libraries, which became very popular back then. By libraries, I mean TensorFlow or PyTorch. And these libraries are equipped with two major features. First one is computation graph that automates evaluation of the loss function for neural networks and do the differentiation of the loss function automatic, which is backpropagation basically. So most of the neural network engineers focus on this part, but as a high performance, say, seeking statisticians, I looked into the second feature, that is the efficient and user-friendly interface to linear algebra routines that work on both CPU and CPU and GPU with a unified interface. That was very attractive feature. And also these libraries support multi-GPU and multi-node computing, meaning cluster, using the same interface. So for example, in PyTorch, it has a torch.distributed interface, which defines a simplified MPI calls. And if the system is equipped with the real MPI libraries, then this simplified MPI calls is converted to the actual MPI calls. So it's quite a good abstraction that these neural network engineers have achieved. And there's also something called CUDA-aware MPI, which maps multi-GPU communication to just MPI calls. So which basically knows what I have done for multi-GPUs using CUDA libraries. But if you have this library, then you can code that what I have done in 2015, just in, say, a couple of hours. Yeah. So to simplify, we can use TensorFlow or PyTorch to write high-performance computing programs that run on both a multi-GPU and a multi-CPU cluster. But you have to read fine print. Yeah, we can. It doesn't mean that it's so easy. The catch here is that those libraries rely on BLAS or basic linear algebra subroutines. In CPUs, that means OpenBLAS or Intel Math Kernel library. And in GPUs, this means a cuBLAS library. And these subroutines are not meant for distributed memory system. It's for just a single memory system. So someone has to write a wrapper code that deal with all the communication between single memory, say, BLAS systems to make a distributed computation done. And there was Seoul, yeah, who did all the heavy lifting. So he wrote this Distomat library, which is available on GitHub, and which basically implements so-called 1D layout for computing matrix multiplication. Say we have A and B matrix, and the outcome is stored in the C matrix. This 1D layout goes like this. We have, say, P processors, and these processors are arranged in a one-dimensional array, say capital P. Then there are three possibilities for matrix multiplication. First one is row partitioning. Basically, we partition both A and B by rows. And then the jth processor owns the jth row block of A and jth row block of B, and computes the jth row block of the C matrix by running this pseudo Julia code, basically. So this is just how you get the jth component of C. But the implication is that because it involves this K index, which is not necessarily available for a processor J, it needs to send its own chunk of B to other processors, and also receive the chunks that other processors own to do this computation. So that means a communication. And another one, column partitioning, partitions both A and B by columns and do a similar calculation, but this time it has to send the chunk of A and receive other chunks of A between other processors. And the final one is inner product partitioning that partition A into row blocks and B into column blocks. Then then processor J owns the jth row block of A and jth column block of B, and compute the jth column block by piece by piece by running this, say, basically code. Multiplying these two pieces, and to do this, it needs to send those parts of A in between the processors. And the point here is that in this distributed computing, there's this local matrix multiplication component, and that can be done using either TensorFlow or PyTorch, because it has a very good interface for single memory matrix computation using BLAS. So a featured problem for that paper was non-negative matrix factorization, which was also featured in the 2010 paper from UCLA. For this problem, there is a very well-known MM algorithm, which has this complex iteration depending on your perspective. It may be complex or sometimes simple. But the gut of this algorithm is that it involves heavily it depends heavily on matrix multiplication. So numerator depends on these matrices, and the denominator depends on these matrices, and these are all matrix multiplication. And using the DistMat library, we were able to do the computation of non-negative matrix multiplication of size, say 10,000 by 10,000, using both GPUs and virtual cluster on Amazon. And for GPUs, we can use single GPU and multiple GPUs. And for cluster, we can just increase the number of nodes. And if we can even increase the size to say 200,000 by 200,000, in that size, GPUs fail to run, but virtual cluster was okay to run, and delivers a result in a pretty short time. So that was the scalability experiment that we were able to do. Okay, the final section is about my recent experiences with supercomputing centers. The motivation for exploring supercomputing, the real supercomputers, is this problem: sparse inverse covariance matrix estimation. So it's another famous problem, but to repeat, the setup is this. We have a sample of size n from p-dimensional random vectors with some distribution, some zero mean distribution with unknown covariance matrix sigma naught. And typical setup is that the dimension p is much larger than the sample size n, and we want to obtain the sparse estimate of the inverse of the covariance matrix, which is usually called omega naught. The reason for doing this is that the sparsity pattern of this omega naught matrix gives rise to a partial correlation graph associated with these p random variables. And probably the most famous one is this model for solving this problem is this graphical lasso problem. The first two terms corresponds to the Gaussian log likelihood, the log likelihood of multivariate Gaussian distribution, and the last term is just a L1 penalty. And this problem has been extensively studied, and there has been many scalable algorithms proposed. But the catch here is they are mostly for the shared memory system, like GPU, and not for distributed memory system. But we had the need to analyze massive scale data, where both the dimension p and the sample size n is so large that using a single machine or a single node is infeasible. So using the distributed memory system or cluster become a must. The data that we wanted to analyze is a multi-omics data. And those kind of data easily takes, say, hundreds of gigabytes of memory, leading to billions of parameters. For example, the dimension of 500,000 is not unusual. And we are dealing with matrix variable of p by p. This involves, say, 100 billion parameters. So it's a huge problem. And then there is a computational trouble, of course. The original graphical lasso algorithm by Friedman and Hasty, right, is based on a coordinate descent. And that algorithm didn't work at this scale. And there is something called proximal gradient, which is an instance of an MM algorithm. This is more parallel-ready algorithm, but there's also a problem. This algorithm involves the gradient of the smooth part of the objective function, meaning the Gaussian log likelihood. But if you take the derivative, then it involves the inverse of the omega matrix, the matrix variable. But this matrix is P by P, say 500,000 by 500,000. And this is an iterative algorithm. So this means that at every iteration, you need to invert a huge matrix. So it's a nightmare. And also, you also not only the gradient, you also need to involve evaluate the objective function. This one. And the first term is a log of the determinant of the omega. And the determinant of P by P matrix, computing that is also a nightmare. So that basically means that the graphical lasso is not an option for this size of a problem. And so here comes Concorde, which is named after a famous ultrasonic commercial jet. Yeah, Concorde is actually a very weird acronym for convex correlation selection method to meet the naming requirement, proposed by a colleague of mine. And this is based on a pseudo likelihood of Gaussian, multivariate Gaussian, and the objective function looks like this. And the difference from graphical lasso is that the log determinant now involves only the diagonal part of the covariance, the inverse covariance matrix. So if this is the case, then the log determinant calculation becomes just a logarithm evaluation problem. So it's much simpler to compute. And if you take the gradient of the smooth part, it involves the inverse of the diagonal matrix, which costs virtually nothing, right? So the proximal gradient implementation of Concorde is called Concordista. And it involves, in addition to the gradient evaluation, it involves element-wise self-thresholding, which is an embarrassingly parallel operation. And also it involves some line search to determine the step size at every iteration. So that's the main idea of Concordista. And there's a high performance version of Concorde proposed in 2018, which is called HP Concorde, which is tested on a supercomputing center, National Supercomputing Center supported by DOE, and tested up to 1 million by 1 million matrix in, say, 5,000 node supercomputer. The main feature, or the main reason that this HP version of Concorde works, is to look at the second part of this gradient of the smooth part of the objective function. The first part, diagonal inversion, costs almost nothing, but now this part becomes problematic. Omega times sigma hat, where sigma hat is a sample covariance matrix. First, you need to build a simple sample covariance matrix, which is P by P dense matrix. And this has to be formed from the data matrix. So it's a dense matrix multiplication. It's a huge matrix multiplication problem. But the good part is that this matrix has to be formed just once before iteration. But what is really problematic is computing this guy, omega times sigma hat. That's sparse times dense matrix, because omega matrix is meant to be sparse, especially when the penalty strength is large. But this computation has to be done because of the nature of a proximal gradient at every iteration. So every iteration, you need to compute you need to multiply huge matrices. So that's a problem. And also you need to take the transpose of the same matrix, which is relatively easy if you are willing to sacrifice some space. So I'll focus on the sparse dense matrix multiplication. In that level of communication between the nodes becomes a major bottleneck. So we need to do every possible measure to reduce this communication. It comes in 3 flavors: layout of how to distribute the data among nodes, and replication. Sometimes you need to make copies of data to reduce the communication at the cost of space. And also you need an efficient algorithm to do the computation. So for HP Concord, so-called 1.5D layout is used, which is basically a layered version of 1D layout that you see in this map. So in 1.5D layout, P processors are arranged as a 2-dimensional array instead of a 1-dimensional array for 1D layout. But the dimension is like a P over C times C. Here, C stands for copy. So you basically copy data. And we specifically use inner product partitioning, meaning that we partition the A matrix by rows and B matrix by column, but now it's the number of blocks is P over C. Then the processor in the array indexed by J and L for layer, owns a copy of jth row of A and jth column of B. And for some number Q, processor J, L computes some of the row blocks of this jth column block of C matrix by using this computation. And then it's sent to do this, it should send the jth row block that it owns to other processors in the same layer and receive the other chunks from the processors of the same layer. So the communication is confined to those processors in the same layer. In that way, the communication is saved. And finally, to get the final result, it does the gather operation in the first layer. And this 1.D layout is particularly effective for Conjugate algorithm or proximal gradient algorithm because it uses element-wise self-thresholding operator. And it depends on the final value of the matrix multiplication. So there are other 1.5D layouts based on, say, row partitioning and the column partitioning, but those partitioning involves reduction, which means, say, some reduction, you have to wait until the partial results are ready, and then you have to sum. So if you want to do self-thresholding, then you have to wait until this reduction operation is finished. So that means some additional latency, but this inner product layout does not have that drawback. So that makes this layout ideal for sparse-dense matrix multiplication for Concord. So now some might have wondered that for this jet, the spelling is Concord plus E. So some might wonder where does E go? So it is very tempting to add E to the name. So I did it for Concord enhanced. So there are some limitations of the original Concord in terms of statistical consistency, because the original Concord proofs need some consistent estimator of the diagonal elements. That's to me, it was a little weird. So I fixed that. And I also got rid of line search. Line search to determine the step size involves additional matrix multiplication. So getting rid of that saves a lot of computation. And also in optimization wise, the convergence is now linear. The original Conjugate algorithm takes sublinear iterations to converge. So linear convergence is something desirable. And the point here is the computational components remain intact in Concord enhanced or Concord, right? So it benefits from the same communication avoiding linear algebra as the original HP Concode. So I would say it's HP Concode E or HP Concode that, right? So I applied that to some data analysis for cancer data, liver cancer data from PCGA. The data is obtained from mRNA sequencing and microRNA sequencing and DNA methylation microarray data. In a nutshell, it's a 300,000 dimensional problem with sample size of, say, 365. And we, me and my colleagues estimated the partial correlation networks using the new HP Concorde, and the computations were done on Korea supercomputer at the Korea National Supercomputing Center with 132 nodes, which is much more powerful than the Amazon virtual class that we used for the previous section. And here is the resulting network. Basically, the analysis was conducted by my colleague at NUS, the National University of Singapore. This shows the network of the whole 300,000 variables, including both methylation and RNA. That's shown in gray color. And also, we also did the network analysis with methylation only, which is in red, and without methylation, which is in green. And you could probably virtually not distinguish the red and green. So my colleague gave me an interpretation. He sent me a very long list of interpretation, but I only put something that I can understand. So the edges identified from this combination of DNA methylation and RNA data did not change the network's overall architecture. So they look pretty much the same at a large scale. But the adjusted analysis, meaning the adding this DNA methylation, produce a little slightly denser connections, and that's probably because the methylation matters more in a specific cell subpopulation, but not that inflation at the whole tissue level. So that's probably the reason that those two networks are not very different. And also we can identify some different communities. So that has also some interpretation of a cell cycle, DNA maintenance, and anabolism and catabolism. I'm not going into the details because I'm not an expert on that. So to conclude, I have gone through my experience with using HPC, high performance computing, for statistical computing, mostly for high dimensional MM algorithms. And this was a journey to meet the scalability need that I faced, starting from single GPU, then to multi-GPU, then a virtual cluster with a few nodes, and supercomputer with many nodes. And this was also at the level of computational complexity. At the lowest level, embarrassingly parallel operations like soft thresholding. For that, single GPU probably would be okay. And then matrix vector multiplication usually arises in regression problems. And for that, single GPU is okay. And if problem size is bigger, then we might consider multi-GPUs, but that time we need to consider distributed version of matrix vector multiplication. And then for problems like non-negative matrix factorization that needs heavy matrix multiplication, 1D layout for distributed computing may be effective, like in DistMap. But in graphical models, that was not enough because communication becomes a real bottleneck. So we need to invent some creative layout for distributed computing. This is for actually communication avoiding linear algebra And it seems that these sort of algorithms have been relatively unnoticed in the statistics community. So it might be a fruitful avenue to explore. And my final take-home message is to work in team. Not a single person can cover all the spectrum of this computation and statistics. So finding a good teammate would be very, very encouraged. So thank you for your attention. And this is my acknowledgement. Seyun did a lot of work. And Songdong, my current PhD student, did a lot of work for this HB Concord project. And also Joshua Bang from UC Santa Barbara. So the faculty members of UCLA, Hua and Joong-Ho, did a lot of work for the virtual cluster project, and Sang-Yun Oh and UC Santa Barbara is the guy who invented this Concord method, and Hyung-Won Choi from Singapore did this biological help. And the National Supercomputing Center of Korea gave me generously a lot of CPU hours so that I can do the computation for free. Thank you.
Quick question.
Yes, sir. Yeah, so as with almost every complex large-scale computing, you can do what you want. In the end, you always get some answers.
Right.
You know the answers are correct. How do you have concern about that when you do all this interfacing and all these things? So that's my question. How do you get a sense that is doing exactly what you want to do and the answers are more or less correct?
Yeah, that's a good question. So going back to this network, so for interpretation, I think we need input from the domain experts. But before going to that, because it's a model selection problem, we need a way of good model selection. So what I omitted for this HB Concord project, the presentation was how to select this the lambda parameter, the penalty strength. And we also developed some Bayesian information criterion based one, which turned out to be quite effective in giving this kind of networks. So that might reduce the burden of the computational biologist to look at the data and interpret the results.
Questions?
When you're working with TensorFlow, have you actually noticed these kinds of problems, issues related to working in single precision coding form?
Oh yeah, that's a good question. So we didn't have much trouble with single precision except for the Cox regression problem, which is not shown here. For that, we need to switch to double precision that slowed down the computing like four times, but it was reasonably fast for us. So if the precision is a real the question, then you might use a double precision option for GPU at the cost of some slowdown. And for cluster computing, because it uses CPUs, there is no such problem. Thank you.
I also have a quick comment. The same code actually is on job market if you want to. You're looking for people from other university, you're looking for someone who knows statistical theory and can do this kind of stuff.